First, thanks to the organizers. Like, it's such a great workshop. There are so many great game theorists in here, which also brings me to the realization that actually two of you might have been the reviewers for this very paper. You might have given me a hard time, me and my co-authors, but you made the paper better. Yeah, so today I will talk about the evolution of noisy learning in games. The title itself might be unclear. I hope by the end of the talk it's clear what I mean. This is joint work with Marta and with Fernando. Most of the work was done by Marta. I hope I do her justice. All right. Let me start with a very caricature what evolutionary game theorists are actually doing during our work time. So usually we start with something that resembles a game, like, for example, here, the prisoner's dilemma. And then we assume that players are perhaps not perfectly rational when playing this game. Rather, they start with playing some strategy in the beginning. Like, for example, here we have a population, like 2 of them play defect, 4 of them play corporate. They get some payoff or some fitness. And then over time, what happens is that, for example, perhaps this blue person here thinks, wait a little, like I get a payoff of 0.8. This red person gets a payoff of 2.4. Perhaps I'm a little bit unhappy with the payoff that I get. So why not switch? And then as a result, the population changes. As a result, actually also the payoffs change, like actually the whole fitness landscape changes. So that's in a nutshell what evolutionary game theory is about. And what I would like to do today is a little bit to look at this particular step where the arrow is. So what happened at this arrow? So what happened is that this blue type compared its payoff to the red type. And because the payoff 2.4 is larger than 0.8, this blue type decided to switch strategies. Okay. And how we model this usually in our models is like we assume that there is some increasing function, like often it's a Fermi function, that just maps. Like I look at my payoff, I look at Josh's payoff, for example, and if his payoff is, for example, in this case, 1.6 higher, I switch with a certain probability, which is an increasing function of the payoff difference. Like in this particular case, I would switch with a probability of 96%. Okay. And so one crucial thing about actually this family of functions is that it has this free parameter, which is called strength of selection. Like it's like here I use beta for this parameter, and it kind of changes the slope of this Fermi function. So for example, when beta is very small, then usually like the slope is very small. You almost get a flat function. So you could say that learning is very noisy because like kind of irrespective of what the true payoff advantage of the other strategy is, you always imitate with a kind of constant probability, okay? Like you're not really driven by the payoff differences. You're not really thinking about like, will it actually help me to adopt this strategy? You just randomly switch more or less. Now, when beta is very large, it looks very different. Like then you get almost this step function, and you kind of switch even only if the other strategy is better for you. Okay, so usually also like when beta is very large, like game theorists, some game theorists like this limit, for example, because the solutions that you get are usually in line with Nash equilibria or so. Like also this limit, by the way, has advantages because here you can use Taylor expansions and this kind of stuff. So here the math becomes kind of easy sometimes. What is important here is that usually beta is taken to be a parameter of the model, so we are not interested in beta itself. Also, we usually assume that it's fixed and the same for everyone. Okay, and so what we would like to ask actually with our paper is like, what happens if people actually differ in their strength of selection? And in particular, like if I have a higher beta than you have, would I be able to take systematically advantage of you? Like, would I be able to get a systematically higher payoff than you get? So that's one question that we have. And the other question that we have is like, if this beta itself was allowed to evolve, like perhaps on a slower time scale, where would it evolve to? Like, would it actually evolve towards weak selection? Would it evolve towards strong selection? That's the question that we have. And so to address these questions, like now I tell you how the talk looks like. Like first, I need to tell you a little bit how we model learning. And for that, I use a particular learning process called introspection dynamics. And then in the second part, I will talk about evolution of noisy learning. Okay. So in the first part, actually beta is still fixed. In the second part, beta is allowed to evolve. All right. Yeah. So let me talk here about the simple learning process. Like it's perhaps the simplest learning process that we could come up with. So instead of a population of players, at the moment we are only looking at two particular players who play this matrix game. Okay. So there's a blue guy, there's a red guy. At the moment, the blue guy cooperates and the red guy defects. And how this process then works is that you randomly choose one of the two players, for example, here the rogue player. You give this rogue player an opportunity to revise its strategy. And to revise its strategy, the blue person here, like at the moment, the blue person gets a payoff of -1. The blue person realizes by switching towards D, I would get a payoff of 0. And then this rogue player also realizes, 0 is better than -1. So with a certain probability, this blue player actually switches from cooperation to defection. So here this actually happened. So the rogue player indeed switched. And now the process just starts anew. Like again, you would choose randomly one of the two players. This player then gets a chance to revise its strategy and then would possibly switch strategy. Okay. And what this gives you is we end up with a Markov chain again. So in this case, for example, what is nice about this process is that there are only 4 states. So either both players cooperate, one player defects, the other player cooperates, or for example, both players defect. For example, if I'm here, if both players cooperate, I can calculate pretty exactly what's the likelihood that I end up here. Like it needs to be the case that player 1 needs to be chosen for an update. It needs to be the case that player 1 finds it worthwhile to update. Okay, so I end up with a 4x4 Markov chain. Yeah, and if I want to know what evolution does in the long run, like what is the long run probability that I observe each of these 4 states, I just need to compute a left eigenvector of this Markov of this matrix. Also, what is nice about this process, but I won't need it here, is that it works for symmetric and asymmetric games alike. Yeah, and I mean here, and actually throughout the talk, I will only work with these 2x2 matrices, but you can actually do the same thing with arbitrarily many actions. Yeah, so this is the learning process that I will focus on. Like it's quite similar to the pairwise comparison process for people who know that. The advantage is that the pairwise comparison process that scales with population size. So if you want to do a Markov chain there, like it can be complicated. Here it's always a 4x4 matrix. Yeah, so back to our original questions. So the first question is, what if people differ in how effectively they learn? Like, so again, you do this introspection dynamics. You have 2 learners who continually update their strategies, but now one has a larger beta than the other one. Would this one player have an advantage in the long run? And it's always good to start with an example. So that's what we did. We start with this prisoner's dilemma. And in the beginning, let's make it simple. Let's assume that both actually have the same selection strength, which in this case is 2. And here you can see what happens. So what happens is that because beta is finite, there will be some times in which they actually both cooperate. But you also see that actually most of the time they both defect, which makes sense because in a prisoner's dilemma, defection is a dominant strategy. All right, now a question for the audience. What do you think happens if I increase selection strength, but for both? Like instead of 2, I will have 5. What do you think happens? Like how does this probability distribution change?
I put more density on DD.
That's right. That's also what I would expect. In fact, I know. And your expectation is totally correct. So once they are more effective learners, once they are better in telling that D gives them a higher payoff, I mean, they will play more DD. All right. And now another question for the audience. What happens if now one player has this high selection strength and the other player has this small selection strength? What do you think happens?
I guess more on CC.
Yeah, compared to this here.
Yeah.
Yeah. All right. All right. What you see is indeed there is a little bit more CC here, but also what you see is that still the one with the higher selection strength will defect quite often. The one with the smaller selection strength will actually cooperate quite often still, like at least with kind of 25%. So as a result, actually you see quite a bit of DC here. And as a result, if you compute the players' payoffs, like the one with the high selection strength has a payoff of 0.341. The one with a small selection strength will actually have a negative payoff. So you see here that in this example, the player with the highest selection strength actually outperforms the one with the lowest selection strength. Okay, this is another way to represent this. This is now a super game. Now the things that the players can choose are no longer between C and D. It's rather between selection strengths. And for example, this number is this one. What happens if both learn with the same selection strength, with the same selection strength of 2, right? And now if you stare at this super game, what is it that you see? It's again a prisoner's dilemma. Like both would actually benefit from having a small selection strength, but actually both individually prefer to have the larger selection strength. And in the end, everyone has a large selection strength. Okay? So this is the first example. Yeah, just to sharpen our intuitions, here's another example, the snowdrift game. Yeah, perhaps before I start with something, let's again assume that in the beginning they have the same selection strengths. Where would you believe that we are in this 4x4, in this 2x2 diagram? Again, like most mass is put on the Nash equilibrium actually. Like, for example, if one player plays D, the other one plays C, this is a Nash equilibrium. When people just learn to play this game, like most of the time they will be on one of these Nash equilibria. But of course, because beta is finite, sometimes they will be off the Nash equilibrium. They will be more often here than they will be here. And most of the time they will be here on one of these off-diagonal states. All right? Now, again, assume that both players have the same selection strength, but now make selection strength even stronger, like increase beta. What do you think happens? Yeah. So probably there is even more time spent on the Nash equilibria, right? And this is also what happens. Like if I increase selection strength for both, like now with 90% probability, I am in one of those Nash equilibria. Obviously, because the game is symmetric, I'm as often in this one than in this one. And most of the time, I'm in one of the Nash equilibria. So what do you think what happens now if one player has a high beta and the other player has a low beta?
They get the better end of the Nash. The one with the high beta gets the better end of the Nash equilibrium.
Yeah, that's what you hope. It's not what happens. It actually turns out that, so here there is a player with a small selection strength. Here there is the player with the large selection strength. It turns out that most of the time, the player with the small selection strength defects. The other one cooperates. So that's actually the Nash equilibrium that favors this player. So in particular, like the player with the smaller selection strength has a higher average payoff than the player with the high selection strength. Okay? And if you again look at the super game, this is how it looks like. Yeah, if you stare at this for not too long, you will actually see that this time it actually, the dominant thing is actually the small beta. Like this is better than this, and this is better than this. So actually in this 2x2 super game, it actually pays to have the smaller selection strength. Okay, so now we know, like we addressed this question here, like what if people differ in how effectively they learn? Would people with large beta always outperform the ones with lower beta? The answer is no. Like there are games in which actually there is an advantage of having the low beta. Okay. And just to remind you, what does it even mean, low beta? Low beta means that sometimes I actually adopt an action that is not good for me in my immediate interest. So I kind of am an erratic learner. Yeah, so the second question now is, okay, now that I've seen these results, beta was still fixed in my examples. Now I let beta evolve. So the question is, where does beta evolve to? So what we do here is actually, now we consider a whole population of players with possibly different selection strengths. They randomly run into each other and then they play their games with each other, like over consecutive periods, modeled with introspection dynamics. And based on these interactions, they earn some long-run payoff. And then, like just as in usual models, we assume that those players with a high payoff, with a high fitness, are more likely to reproduce, and the offspring inherits their beta plus minus some small mutation. Okay, and also like now beta is actually a continuous variable, so we cannot, we don't have these two types of beta anymore. We have a continuous beta. So now we actually need adaptive dynamics. And you can actually just simulate this process. So how it looks like in the prisoner's dilemma, for example. So this is the very same payoff matrix that I showed you in the beginning. What you see here is evolutionary time now for this long run process where beta evolves. On the y-axis, you see the selection strength and where it evolves to. What you see for this prisoner's dilemma is that players learn to have higher and higher beta. Like they want to have more, and they want to be more and more effective in the learning, because the better they are in the learning, the more likely to play D, and playing D is just the optimal thing in the prisoner's dilemma. Yeah. Oh, yeah. Thanks. You could also look at pairwise invisibility plots. Then you would see that, like the way how to read this is, so if this is the resident, the gray area shows you which kinds of mutants are favored to invade. You see everything above the diagonal is always favored to invade. So that's just another way of showing that you want to have larger and larger selection strengths in this evolutionary dynamics. Now, the second example is the snowdrift game. And perhaps if you've never seen this before, this might be surprising. But after what I've told you before, this might not be surprising anymore. Here, you don't observe that beta is increasing and increasing. Rather, it converges to some finite value. So here, there is a finite ESS. In the end, everyone will have a finite selection strength. And so in particular, like there will be some noise in your learning. Okay? And the last example is like even something more complicated can happen. Like this here now is a stag hunt game. And for the stag hunt game, you also see that initially it converges to some singular strategy, which is finite. But then actually there's evolutionary branching. So some individuals just evolve to have higher and higher betas, but some individuals just have a constrained beta. Okay. Yeah, and now I've always shown you 2 or 3 examples. You might want to know, okay, how general is this phenomenon? So we looked at this general parameterization of 2x2 games where you have these 2 free parameters, A and B. And you can ask yourself, okay, like where will I see which case? And what you get is this kind of graph. So you will see for most of the, like white here means that you have selection towards infinite beta. So for most prisoner's dilemma, you will see selection strength to increase indefinitely. But for snowdrift games, you see usually a stable ESS. For stag hunt games, at least for this upper half, you will see that there is evolutionary branching. So it's not that I like handpicked these 3 examples, but like this is a robust phenomenon. Now, you might also say that introspection dynamics, man, I mean, that's something that you came up with. I don't trust your process. Perhaps it only holds for introspection dynamics. That's also one thing that one of the reviewers correctly argued. So actually, we tried different processes. We also tried some versions of reinforcement learning or of some, so these are 2 reinforcement learning processes. This is something fictitious play. And you see that they always lead to these pairwise invisibility plots that would predict a finite beta. All right. Yeah, so the take-home message is just as we use learning processes to study which actions players choose, like cooperation or defect, we can also use evolutionary process to actually study like the evolution of these parameters of these learning processes. And using this meta perspective, you find that sometimes seemingly suboptimal learning behavior can evolve because it gives you a strategic advantage. And with that, thanks again to Marta and Fernando who helped tremendously with this. In fact, I was only the messenger. Yeah, I hope I did Marta justice. Yeah, thanks.